Welcome to Spring LIB.
Hello everyone, today we're doing chapter 11 problem 48, and this problem gives us several reagent schemes and asks us to identify the unknown intermediates and unknown reagents used in the following reaction. So let's see what we start off with. Well, we begin with a compound that has an alcohol group and have some sort of ester group here as well, and we have some alkene bonds here. So what we reacted with first is PBr3. So if you guys remember from past, PBr3 changes an alcohol, which is a bad leaving group, into some sort of halide, this one being bromine, which is a good leaving group. We know that also the alcohol could react with something like Sokal to change this alcohol to a chlorine, but PBr3 does the same thing. So we know that oxygen being electron rich and nucleophilic, it can attack your electrophilic phosphorus center, making a bond. When you make a bond, you break a bond. So one of these bromine groups will fall off, picking up with 2 electrons, become Br minus, a bromide anion. So now your bromide anion can act as your nucleophile, being electron rich in nature, and do an SN2 backside attack to kick off now your good leaving group, which is the oxygen attached to this phosphorus core. So now essentially what happens, we change this OH group to Br. So we would get product A, which is now making a bad leaving group into a very good leaving group. Which would be A. So now we're taking A as a starting material and we're reacting with some sort of reagents here. So if we identify what's your reagent, what's your reactant. So your reactant is this and your reagent is this. So you have a reactant, which is some sort of alkyne, and you're reacting this alkyne with some sort of salt here to get B. And then what we're doing is we're taking A and reacting it with B. So if we identify, well, what do we have here? We have some sort of carbanion here, and we have a lithium counterion, which is just a spectator. It doesn't really do anything, this lithium. So we know that this CH3 minus carbon would have extra lone pair electrons, making it very, very, very reactive, very good nucleophile. So we know that this could potentially pick up an extra proton to neutralize itself to make methane gas, and in the process make another strong carbon anion, which is going to be a strong nucleophile. So let's see what acidic protons we have here. Well, the only protons we have here is this blue one here off the alkyne, and this CH2 here, part of this hydrocarbon chain. So we know that this proton off the alkyne is very acidic. What does acidic mean? It means that it's okay for this carbon atom to lose this proton. And the reason it's okay for it to lose this proton is because of the 50% s characteristics around this carbon orbital. So it's sp orbital. We have 1, 2 substituents. So it's s1p1. So 1 plus 1 equals 2 different things bound to it. So we know that this is an s orbital, sp orbital. So this has 50% s characteristics, meaning that the conjugate base, so when it loses this proton, the conjugate base is going to be highly stabilized. So those lone pair electrons are very close to the small to the atom's nucleus, because it's going to be localized in the smaller s orbital. So we know that because of the stabilization of its conjugate base, this is what we call an acidic proton. So we know that this CH3 minus is going to pick up this proton to make methane gas and a new carbanion off this alkyne to make now our strong electrophile, which can obviously do an SN2 attack to kick off this very good leaving group on this electrophilic carbon. So we make a bond and then we break a bond to give us product C. So this is A. Now let's move on to B. So what do we have in B? Well, we start off with some sort of epoxide which is going to be an electrophile, and we're reacting with D and water to get an epoxide ring opening. So we know that this epoxide must act as our electrophile, so D must be a nucleophile. So we know that the nucleophile will attack on the least sterically hindered carbon. Well, which one is that going to be? Well, both of these carbons have one proton, and so you would assume that they're equivalent. But now let's look at the identity of their substituents. So on the left we have a methyl group, and on the right we have a CH2 OR. So we already have greater number of atoms on the right side than the left. So we know that the left side is going to be your least sterically hindered site. So we know whatever the nucleophile D is going to do a backside attack, so opposite from your epoxide, making a bond. When you make a bond, you break a bond, and those 2 electrons goes to the oxygen nucleus, making an O minus. But that's when we reacted with water. So then that O minus can pick up a proton to become this alcohol group we see here. So what's the identity of D? So we know that this is the oxygen of the epoxide that opened up. This is the OR. These are the 2 carbons that could have been potentially attacked. This is the original methyl group. So we know that we added this group, this alkyne group. So let's draw that alkyne. But how do we make an alkyne nucleophilic? Well, just like in the example above, we need to add a lone pair of electrons to make it a carb anion, making it a very reactive nucleophile. So this is what the identity of D to make this compound is. Then we kick off this R group to make an alcohol, and then we take one of these alcohols and we make this bad leaving group, which is an alcohol, into a very good leaving group, which is an O-tosylate. So we have 2 alcohols. We have this right one and the central one. What's the difference between these 2? Well, the right one is a primary alcohol, while the middle one is a secondary alcohol, if you guys can see there. So obviously, your primary alcohol is going to have greater electron density around this oxygen nucleus, so it's going to be a stronger nucleophile than this one over here that has stabilization due to these 2 substituent groups. So we know that this primary alcohol is going to be a stronger nucleophile with more electron density around its oxygen nucleus, and it's going to react with a tosylate or a tosyl to make a tosylate group here, an O-tosyl group here. So we know that we need to add a tosyl chloride, and specifically we only want one equivalent because we only want this one to react. And if you guys remember what tosylate looks like, it looks something like this, with the chloride being your leaving group. So the oxygen being nucleophilic will attack the sulfur atom, making a bond. When you make a bond, you break a bond. So one of the pi bonds of this carbonyl groups will collapse to give you O minus, and then one of the lone pair electrons will go back down to reform your carbonyl, making a new bond. When you make a bond, you break a bond, so your chlorine falls off. And now we have an O attached to this substituent here, hydrogen and sulfur, so this oxygen would have 3 bonds. So we positively charged, but we want this oxygen to be neutral with its proton being ripped off. So what do we add? Well, we add a proton scavenger being pyridine. So we add pyridine, which is a proton scavenger, and it will remove this proton, and we'll get this final compound here. So now we made a very good leaving group, and now we reacted it with something to give us an extra carbon. And now we have this starting material, which we're reacting with sodium hydride and F. Well, let's see what sodium hydride does. Sodium hydride, remember sodium is your spectator ion, doesn't really do anything, it's just the counter ion for this hydride. So hydride is a negatively charged hydrogen. So what this is a very reactive, you can say, nucleophile that will rip off any protons to make neutral hydrogen gas, H2 gas. Hydrogen does not like being negative, so this is very reactive to deprotonating stuff to make whatever deprotonates into a strong nucleophile. So we have 2 protons that we consider acidic. We have the alcohol proton and this alkyne proton. But this alcohol proton with its much larger pKa is much more acidic than this alkyne proton. So we know that O minus is going to be more happy. The conjugate base of OH is going to be O minus. This is a lot more happier than a C minus. So why? Because oxygen is more electronegative than this carbon. So what does that mean? Oxygen is happy to carry those 2 extra electrons on its nucleus than a carbon would be. So we know that the stability of O minus is far greater than stability of C minus. So we know that this hydride will rip off this acidic proton first to give us O minus, and then we're reacting O minus with some sort of F to give us this product here. And actually, because we're given the product, it also tells us which hydrogen is being ripped off to make it a nucleophile. So you would have 2 options, O minus or C minus, but the product tells us that O minus is the correct nucleophile. So that's a nice validation to do as well. So we know that we're adding 2 carbons. So we need to draw 2 carbons in our electrophile because oxygen would be our nucleophile. And then we're going to add some sort of leaving group that when oxygen attacks this carbon, the leaving group will fall off. So we can add any halide, I'll say bromine for this case, and then we'll add our 2 carbons to make this starting material, which we reacted again with sodium hydride, but now we only have 1 acidic proton, which would be ripped off to make a carb anion, and we'll react in this carb anion with this electrophilic reagent here to make a bond, and we're going to kick off our halide to make our final product, which is this.